Okay, pH, lowercase p, capital H. The definition of pH. pH equals minus log to base 10 square brackets concentration of H plus. Okay, H plus is aqueous. Right, so that's the definition of pH. If you want to work out the concentration of the H plus, then it's going to be 10 to the minus pH. Okay, so that's how you work out pH. How do you work out pH specifically for strong acids? Okay, pH for strong acids. Okay, so if you say, for example, we've got nitric acid solution, concentration 0.005 moles per decimeter cubed, and I want to find out the pH of this solution. Strong acids fully dissociate into ions, fully split into ions. The word is dissociate, which just means split up, dissociate into ions, into hydrogen ions and the nitrate ions. Okay, so if the concentration of the acid is 0.005, the concentration of H plus is going to be exactly the same, 0.005. So then you can work out the pH, which will be minus log to base 10 of 0.005. And when you do that calculation, you get a pH of 2.30. Now for pH, you normally have 2 decimal places, and there are no units. Okay, so that's how you work out the pH of a strong acid. It's quite straightforward, fully dissociated. That's the concentration of the acid, and that's the concentration of the H plus. You've got to watch out, this is 1 to 1, it's a monobasic acid, but if it's a dibasic acid, if it's 1 to 2, then you've just got to be careful of that ratio. Okay, that's how you work out the pH of strong acids. How do you work out the pH of weak acids? pH of weak acids. Okay, so let's say, for example, you've got some ethanoic acid. Concentration, let's say 0.1 moles per decimeter cubed. Okay, now a weak acid partially dissociates into ions, so it's in equilibrium, so it partially splits up into ions. So you've got the ethanoate ion and you've got the H plus ion. Okay, so if you have 0.1 moles per decimeter cubed of the acid, what's the concentration of the H plus going to be? Well, it's 1 to 1. One of those makes one of those. So you would think that it was 0.1 moles per decimeter cubed, but it's not, because only a very small amount has dissociated, has split up. So you cannot use the same method for weak acids that you use for strong acids. You have to have a different method. And this is where we need to use an equilibrium constant. Now you've already studied Kc, equilibrium constant, but due to concentration, but this is Ka, and this is called the acid dissociation constant. The acid dissociation, so my writing's not very good, constant. And it's just like Kc, okay? Ka is the products divided by the reactants. So the concentration of the product, and then you times them together, divided by the concentration of the reactant. Square brackets, make sure it's square brackets. That bracket is not very good, make sure it's square brackets. You don't have to put the state symbols in, it's all aqueous. Okay, so it's just like Kc, okay? But it's another equilibrium constant. It's Ka, called the acid dissociation constant. Now normally they give you the value. Every weak acid will have its own Ka value, and the exam question will normally give it to you. Okay, so for this case, for ethanoic acid, the Ka value is 1.7 times 10 to the minus 5, so it is a very small number, and it's in concentration. Can you see that the units are just concentration? Because you've got 2 concentrations on the top and 1 concentration at the bottom, so the units are just concentration. Right, you do some what we do now is some approximations. Okay, we make some approximations. The first approximation that we make, okay, is that we say, because we've got one of these, and when it splits up, we're going to get one of those and one of those, the same number. We make the approximation that the concentration of the ethanoate ion, the salt, equals the concentration of H+. Okay, because it's 1 to 1, so those should be the same number. So we say that they are the same concentration. Now this is not exactly the case, because there is water present, and water will very slightly dissociate and split up and generate H+ ions, but that's quite negligible. It's quite a small effect, so we make the approximation that that equals that. Okay, right, another approximation that we say is, we say that the concentration of the acid, at equilibrium, because remember that this is at equilibrium, is equals the same as the concentration of the acid initially at the start. I just put initial. Okay, so that's the second approximation that we make. We say that hardly any of this has split up, has dissociated. Okay, so we make this approximation, these 2 approximations. So once we do this, we can rewrite this Ka. Okay, so we can rewrite the Ka. So let me just quickly, actually I might just squeeze it on the bottom down here. All right, so if we know that Ka is 1.7 times 10 to the minus 5, okay, and we know that that equals that, so then what we can do is we can just put H+ there instead. So we've got H+ times H+, which is H+ squared, H+ times H+, yeah, and then we divide it by the concentration of the acid, and we're saying that the concentration of the acid is the same at equilibrium as it was initially, and our initial concentration is 0.1. Okay, so this is to find the pH of a weak acid. We rearrange, we take this up and times it. I'm going to do this on a separate piece of paper. So what we've got is, we've got 1.7 times 10 to the minus 5, which is the Ka value. We've got H+ squared over 0.1. We rearrange, so H+ squared is 1.7 times 10 to the minus 5 times 0.1. Okay, then we square root to get rid of this, so we square root it, and that will give us the H+ concentration. Okay, so when you do that on this example, you get 1.304 times 10 to the minus 3 moles per decimeter cubed. Okay, and then you can work out the pH, because you can just do minus log of that, and when you do minus log of that 2 decimal places, you get 2.88. All right, so that's how you work out the pH of a weak acid. So let's just double check. pH of a weak acid, you can't use the same method because it's partial dissociation. You've got to write an equilibrium constant called the acid dissociation constant, which is the products divided by the reactants. They give you the value. We are going to say that that equals that equals that, because it's 1 to 1. We're going to say the equilibrium concentration is just the same as the initial concentration. So we can go like this here, okay, and then we can work out the pH for a weak acid. So that's the method for a weak acid, okay. Next, so that's the pH of a strong acid, the pH of a weak acid. Well, before we move on, let's just quickly look at Ka. You've got to remember that Ka is just like Kc, okay. So the value of the acid dissociation constant, the value of Ka will depend upon temperature. So in the exam questions, normally the temperature is 25 degrees or 298 K, but they will specify the temperature because the value depends upon temperature, because an equilibrium constant is only constant if the temperature is constant. And if you think about it as well, the larger the value of Ka, what does that tell you about the strength of the acid? The larger the value of Ka, the larger the value of Kc, that would tell you that the equilibrium lies further to the right. The equilibrium lies further to the right, and therefore there's more dissociation. It's just like Kc, greater dissociation, and therefore that tells you the stronger the acid. The stronger the acid. Okay, so the larger the value of Ka, the stronger the acid, right? So if we take, let's compare. If we have two acids, right? So if we have ethanoic acid, for example, right, which has a Ka of 1.7 times 10 to the minus 5 moles per decimeter cubed, okay, and if they compared, if the question compared with another acid, let's say chloric 1 acid, which has a Ka of 3.0 times 10 to the minus 8 moles per decimeter cubed. Now, which of these acids is the stronger acid? They're both weak, but which is the stronger acid? Well, the one with the largest Ka, is the strongest acid. Okay, so can you see that this one, the largest Ka, will actually be this one? So this is the strongest acid, ethanoic acid. All right, but can you see that we're dealing with very small numbers here, times 10 to the minus 5 times 10 to the minus 8. So just like pH, we can use a more manageable scale. So we use pKa. So pKa, small p, is minus log to base 10 of Ka. So whenever you see the p, it means minus log. Okay, so if we did minus log of Ka, it gives us a pKa value. And when you do that for each of these examples, this number, this really small number, 1.7 times 10 to the minus 5, becomes 4.77. And the small number 3.0 times 10 to the minus 8 becomes 7.52. So all of a sudden, by doing minus log, you're making the numbers a lot more manageable. Okay, so the strongest acid, not strong, they're both weak, but the strongest of these two is ethanoic acid, because it has a small, has the largest Ka and the smallest pKa, because it has the largest Ka and it has the smallest, oh, the writing's gone completely wrong, because it has the smallest pKa. Okay, so that's how you compare the acids. Ka, largest Ka, equilibrium furthest to the right, greatest dissociation, stronger the acid. Smallest pKa will be the same thing. Okay, right, so that's how you work out the pH of strong acids, how you work out the pH of weak acids. The last one to do is the pH of strong bases. Okay, the pH of strong bases. pH of strong bases. Okay, so let's take for example, sodium hydroxide is a good example, right? So you said sodium hydroxide concentration 0.075 moles per decimeter cubed, and I want to work out the pH of that. Now, as soon as you see pH, you know that you need the hydrogen ion concentration. That's what you need, because pH is minus log 10 of the hydrogen ion concentration. So it's a strong base, so just like a strong acid, it partially dissociates into ions, like that, okay? And because it's 1 to 1 to 1, and it fully, did I say partially? I meant fully, not partially, fully dissociates into ions. Okay, so the concentration there is exactly the same. Okay, but that doesn't help us because we want H+. So we need to use another method. Okay, now this other method, water. Okay, if you take some water, very slightly, the water ionizes. Okay, so if you take some water, then very slightly it will split up, very slightly it'll split up into ions. Okay, and we can write a Ka for it, or Kc. Ka is the right hand side, the products, divided by the reactants. Okay, does that make sense? Yeah, and then if we rearrange and we get Ka times the concentration of water, and then don't forget water's a liquid, the other two are aqueous. Okay, because hardly any of the water dissociates, the concentration, if we do an approximation and we say that the concentration of the water is effectively constant. Okay, because hardly any of it splits up. So this is a constant, effectively, an approximation. So a constant times a constant. A constant times a constant is a new constant called Kw. Okay, there's a capital K and a small w. So Kw is H plus times OH minus. Kw's got a name. It's called the ionic product of water. The ionic product of water. It has at 25 degrees, like other equilibrium constants, it has a value. You don't have to remember it. Well, not for OCR exam papers, they put it in the data sheet. The ionic product of water, it's 1.00 times 10 to the minus 14. Because it's concentration times concentration, the units are a little bit weird, so just be careful. Mole squared dm minus 6, and it's that's at 25 degrees. Its value will change depending upon the temperature, okay? And it's called the ionic product of water. Now, just think back to our original question. We're trying to find the pH of a strong base. We need H plus to find the pH. We've got OH minus. We've got OH minus. So we can just put the OH minus, can go into here. We've got Kw, and we can find H plus. So that's how we do the question, all right? So let's just try it out then. So Kw, you know, is 1. I'm going to lose the 0, but they are there, but I'm just going to leave them for a minute. The Kw is H plus times OH minus. The OH minus, the hydroxide concentration is 0.075. 0.075. Rearrange that to give us H plus equals 1 times 10 to the minus 14 divided by 0.075, which gives a H plus concentration of 1.33 times 10 to the minus 13. Then work out the pH. You just go minus log to base 10 of that, and that equals 12.88. So the pH of a sodium hydroxide of that concentration solution will come out as 12.88. And we use this method called the ionic product of water. Kw is H plus times OH minus. Okay. Let's just do another example quickly, just to show it. You've got to watch out if it's, say, 1-to-1. So say, say if it was like, for example, calcium hydroxide. Okay, calcium hydroxide. So we say the concentration is 8.75 times 10 to the minus 2 concentration of calcium hydroxide. You've got to be careful here because it is not 1-to-1. All aqueous, but when it splits up, it's going to be 1-to-2. So the concentration will be 8.75 times 10 to the minus 2 times 2, which is a concentration of 0.175. So it's not 1-to-1. And then you do the same idea again. You go Kw equals H plus times the concentration of the hydroxide ions, H plus, we rearrange it, 1 times 10 to the minus 14 over 0.175 gives a H plus concentration of 5.71 times 10 to the minus 14 concentration. And then you work out the pH, you go minus log of that answer there, and that gives you a pH of 13.24. So that's a 4. 13.24. Okay, so that's how you work out the pH of a strong base. There is a shortcut as well. Let me just show you a shortcut. There is a shortcut. Let's use the sodium hydroxide example for the shortcut. Okay, so there's another way to do this that can be a bit quicker. So remember with the sodium hydroxide, we've got that concentration and it gives a pH of 12.88, right? So there's a shortcut. P just means minus log 10. So POH is minus log base 10 of the concentration of the hydroxide ions. At 25 degrees, 298K, pH plus POH equals 14. So if it's all done at 25 degrees, then you can use this shortcut. So looking back at our previous example with sodium hydroxide, which was a concentration of 0.075 moles per decimeter cubed, and then we get the hydroxide concentration, which is exactly the same. Then what we can do, pH equals 14, take away POH. So we can do pH equals 14, take away minus log to base 10 of the OH minus concentration, and then that gives you, so this is without using Kw, and that will give you exactly the same pH, 12.88. Exactly the same. So this is a shorthand method. Okay, so when you see the P just means minus log 10, and we use it to make the numbers more manageable. Okay, final point, this is it. This is truly the final point to do with Kw. Sometimes they're quite sneaky in exam questions, and they talk about pure water. Now, when you're talking about pure water, then that means the hydrogen ion concentration equals the hydroxide ion concentration. Okay, so if it was done at 25 degrees, so we know that Kw, if it's done at 25 degrees, then we know that Kw is 1 times 10 to the minus 14. Sorry, that is meant to be square brackets. My handwriting is terrible. H plus times OH minus. Okay. Now, if they're equal to each other for pure water, then they're equal to each other. So you can replace that with H plus. So then you get 1 times 10 to the minus 14 is H plus squared. Then you work out what H plus equals. So H plus will equal, when you rearrange that and you square root 1 times 10 to the minus 7, then you work out the pH, which is minus log of that. So we have pH 7. So the pH of pure water at 25 degrees will be pH 7. Okay, final point, a solution which is acidic. When it's acidic, it means that the H plus concentration is greater than the hydroxide concentration. When it is neutral, it means that the two concentrations are equal to each other. If a solution is alkaline, then it means that the H plus concentration is lower than the hydroxide concentration.